Okay, let's do a little bit on graphics, and then we'll see how we're doing with time. So there's some readings for this week. The required readings are the readings that you need to do to kind of understand the material in the lecture and in the homework. The additional supporting materials is other stuff that you should go and look at if you're really gung-ho about getting a high grade in the course. So another way of saying that is, how should I put this? There was a directive from above my pay grade that said, okay, course grades should be assigned in the following way. If everyone does everything that's asked of them, that gets you up to a 79%. And above and beyond the basic requirements is A territory, 80 and above. So the way I'm doing that in this course is the required readings get you up to 79%. And go and familiarize yourself with some of that stuff to go in the above and beyond territory. You don't necessarily have to do all of it, and the homeworks will give you a good inkling about what aspects occupy that above and beyond territory, because in the homeworks they'll also be organized like that. They'll be kind of the 0 to 79% stuff, and then at the end of the homeworks there'll be a little bit of an extra thing that we didn't see in lecture, that maybe isn't in the required readings, but is in the additional materials. Does that make some sense? Okay. All right, let's talk about graphics. Ooh, slides. All right, so, question.
How relevant are like 3 days for the exam?
How relevant are the readings for the exam? Very relevant. Yeah.
Like even the additional stuff?
The exams will be organized in the same way, where if you don't do any of the additional readings, but you do all the required readings, you come to all the lectures, you do all the labs, you can get up to 79%. And maybe if you're clever, you might get a little bit above. But there'll be some stuff in the extra readings that will be tested on the exam in that 80 and above category. Yeah. And as we go, I'll give you some inclinations and hints about what that stuff is as we go. It's not meant to be something where I'm trying to trick you or, it's supposed to be straightforward. So when we're dealing with data, this is kind of a flow chart of how we, as scientists, think about it. We import some data from a study or a piece of equipment. We do something to tidy it up, to clean up the data, and then we enter this loop where we transform the data in a particular way because we're interested in answering a particular question. We visualize that graphically in some fashion. We try to model it with a statistical model to test some ideas. And based on that, we have another idea. And we kind of swim around in this transform, visualize, model loop until we have some answers. And then we communicate. Then we write a paper or a report. And so today we're going to talk about the visualize part of it, although that interacts with the transform part of it a little bit as well. Next week we'll talk more about the transform part of this, where we'll learn some R commands that you can think of as verbs for how to select variables, filter observations, create new variables, and that sort of thing. But today's about graphics. But before we see how to do it, let's ask the question why. Why should we make plots of our data in the first place? Numerical summaries like this are really easy to generate. We can compute averages and just show averages. We can compute standard errors and show those. We can compute correlation coefficients and look at those. There's a couple of reasons why, I personally don't like looking at that kind of thing. It just makes me feel a bit nauseated to see a giant matrix of numbers. I don't know where to look, and I don't know what to focus are pre-wired to prefer, for most of us, graphical depictions of things. Our brains are very good at picking up patterns graphically, not so much in a giant matrix of numbers. The other reason is that when we generate means or standard deviations or correlations, those are summaries of the data. Those are based on taking a whole bunch of numbers and reducing them to one. And so that raises the possibility that we're going to obscure some important patterns in the data. So that's the main point I want to get across in this lecture is always plot your data. Don't just rely on numerical summaries. And I'm going to show you two examples of this. One that's older and one that's newer in Vistilia. This is a set of data called Anscombe's Quartet. Anscombe is the name of the person who made it. And each of these 4 panels, we're plotting the x and y values of some data points. I don't know what they are. So in this panel, you can see the data follow a very, very tight linear trend, and then there's an outlier. In this version of it, there's no linear trend here. All the data with this x value has wildly different y values. So there's no real pattern here. It's a vertical line. And then there's an outlier. In this version, there's a very clear pattern, but it's not linear. It's curved. And in this one, there's a noisy linear pattern. And the crazy thing about this data set is for each of those 4 panels, they all have a mean in the x variable of 9. They all have a mean of the y variable 7.5. They all have a variance of 11. They all have a correlation coefficient of 0.816. And if you were to do a linear regression on those 4 data sets, you get the identical equation. So, in other words, if you didn't plot the data, and I just gave you those numbers, those summary statistics, you would not know which one they came from. And there's, in principle, an infinite number of other data sets that would produce the same numerical summaries. But of course, those 4 data sets are very, very different in how they're organized. And our brains are very good at picking that out. Here's another version called the Datasaurus Dozen. So that's actually 13 different data sets. And you can see just visually, they're wildly different, right? These are all x, y scatter plots. One of them is a circle, one of them is a donut, it's an x. This is just 9 points. These are horizontal lines, vertical lines, diagonal lines, a star, just a cloud, and one's actually a dinosaur. And the crazy thing about these data sets is they all, at least in 2 decimal points, they all have the same x mean, they all have the same y mean, the same x standard deviation, y standard deviation, even the same correlation. At least up to 2 decimal points. So again, based on these summary statistics, you would not know which of those 13 plots I was giving you. And indeed, there's an infinite number of other data sets that would produce the exact same summary statistics. So I think I've made that point now. Don't rely on numerical summaries. Always plot your data because your brains are very good at picking out patterns. Now, in this course, we're going to make plots. We're going to generate graphics by typing in code, by typing in R code and ggplot commands. And it's a reasonable question to ask why. Why would we do that? There are these packages out there where we can use the mouse and the pointer and point and click our way with menus and dialog boxes to generating various plots. So why would we want to do it in code? There's kind of at least four reasons I think of that are important. The first is that it's easily repeatable. If I give you a stats package like SPSS and ask you to generate a plot, and you take a few minutes and you point and click your way through, 13 or 14 steps to generate a plot, you say there, and let's say you're a grad student and I'm your supervisor, you say there's my plot. And I look at it and I say, oh, that's cool. That's really cool. Now, why don't you do it again, but change this line thickness and change the x-axis between this and that. Okay, and you go away for 10 minutes and you point and click your way through that, and you bring it to me and I say, well, that's really cool, that's much better, but why don't you change this? And, there might be 10 or 15 iterations of that. If each time you need to go and point and click your way through it and it takes a few minutes, then, number one, it's time consuming. Number two, it's prone to error. You might inadvertently click through the wrong thing and make a mistake. If your figure is generated with code in a script, and I want you to change the line thickness, for example, you simply go to one place in the code where it says, line width equals 1, and you change that 1 to a 2, and you hit go, and there's the figure in like 10 seconds, right? And indeed, you could give me the code, and I can generate it for myself and have the identical figure. So it's also really easily repeatable and extensible and shareable. It's also durable. I'm old enough now that I actually have a folder that has all my graduate student stuff from the 1990s. And a lot of it's MATLAB code, and it all still runs. Like I can generate those figures from that paper in 1993, and it will still generate, which is pretty cool. I have a bunch of files in Microsoft Word from that period of time, and they will not open. It was some weird previous version of Microsoft Word, and it's changed now. I can't open them. They're just gone. If I had used some old version of SPSS to generate those figures, I would not be able to generate them again. I'd have to go and somehow create like a virtual machine of Windows 95 and go find SPSS, circa 1993. And try to emulate it or some crazy thing, right? Whereas code is usually very, very durable and backwards compatible. R is not going to change so much that code we produce now is not going to be runnable in 5 years, 10 years, whatever. So for science, open science and sharing code is really important these days. And so it's a reasonable way to go. Okay, for graphics in R, we're going to use ggplot, which is a package that's part of this kind of meta package called the tidyverse. So open up RStudio and type in this command into the console, install packages, graphical tidyverse. You just have to do it once, and it will go to the internet and download that package and install it up in R, and then it's installed. Then to actually use it, every time you start RStudio, you have to say library graphic tidyverse. And that will load it from your disk and activate it. You only have to install it once, but to use it, you have to actually tell R load in tidyverse. So ggplot2 is a package which comes with tidyverse. And it includes a whole bunch of stuff. It includes a whole bunch of commands and functions to produce graphics, and it also contains some sample data sets. One of them is called MPG, which stands for miles per gallon. It's a data set of automobiles, cars, and it comes in a format called a tibble. And a tibble is basically just a table. I forget why they call it a tibble. They're kind of confused. But it's essentially a table, kind of like an Excel spreadsheet. It has rows and columns, and it looks like this. So if you just, after you activate the tidyverse, if you just type in MPG, RStudio will spit out that. And so each row is an observation, and each column is a different variable. So there's 234 different cars in this data set, and each car has a value on 11 variables. There's the manufacturer, the model of the car, an Audi A4, the displacement of the engine, the year it was made, the number of cylinders in the engine, whether the transmission is automatic or stick shift, whether it's front-wheel drive, four-wheel drive, or rear-wheel drive, the miles per gallon in the city, the miles per gallon on the highway, and I forget what the other ones are. So we're going to use this as a kind of a fun data set to play around with. If you type question mark and then MPG in the console, you'll get a help page on the side that tells you all about the data set. And like I said, if you just type the name of it, you'll see the first few rows. If you wanted to know how many rows there were, the command nrow will tell you there's 234 cars, and ncol, the number of columns, will tell you how many variables there are. You can also look at a data frame or a tibble using the glimpse command, and instead of showing you rows and columns, it's now showing you columns by rows. It's the same data, just in a different orientation. Does anybody know what these things here mean? CHR, PPL, INT? Any guesses? Yeah?
Like the type of variable, so like character,
That's right.
like integer.
Yeah, exactly. It's the type of each variable. So the model, the manufacturer of the model are CHR, which stands for character. So alphanumeric characters, A, B, C, D, E, 1, 2, 3, 4, 5. DEL and int, those are both numerical types. Int means an integer. An integer is a whole number with no decimal place. And DEL stands for double precision floating point value, which is a mouthful. But essentially what it means is it's a real number with decimal points, not an integer. That's all it means. And there are some other data types that you'll see as we go along, but that's what that column means. If you type view with a capital E, bracket, and then the name of the data set, it'll bring up a kind of a spreadsheet-like view of the data where you can scroll through it using your mouse. It's kind of a handy way of looking at a data set sometimes. Okay, let's say we have a question. Do bigger engines use more fuel? Of course we know the answer is yes, but it's a good sample question to look at. So the displacement variable is a measure of how big the engine is. Larger numbers being a bigger engine. And the HWY, the highway variable, is a measure of the fuel efficiency, miles per gallon. So larger numbers means more fuel efficient. Smaller numbers means less fuel efficient. So let's say we wanted to plot one against the other. Displacement, or highway against displacement. Let's create a ggplot. There, you created a ggplot. Let's talk about how this works. So the first command is always ggplot. And then in brackets, you need to tell it what the data set is that you're plotting. And it's usually a tibble or a data frame. A data frame and a tibble are kind of the same thing. A tibble is a newer version of a data frame. And they're both essentially rows and columns, like a spreadsheet. So we say, I want to make a ggplot, and our data equals npg. Then we say plus, and in ggplot language, the plus kind of means, and then do another thing. And then you want to add a layer, a graphical layer of geom points. So the point means you want dots, and the geom means that it's one type of geometric layer that we're adding to the plot. And we'll see there are other geoms, like lines or bars. So we're going to add geom points. And now this is a bit weird. We need to supply what's called a mapping. And the mapping tells ggplot essentially what do we want to plot on the x-axis and what do we want to plot on the y-axis? So we need AES, which stands for aesthetic layer. And I don't know why, but we need that. We say mapping equals AES, x equals displacement, y equals highway. So on the x-axis, we want the displacement variable, and on the y-axis, the highway variable. And when we enter that command, this gets produced. So it's not much to produce a scatter plot right away. Now there's a background, and the dots are black, and the font is small. All that stuff can be customized fairly easily, but it's a good starting point. So this first command essentially tells ggplot, I want to make a new plot with this data set, and it creates a coordinate system. The geoPoint command says, I want to add a layer of points. And this mapping command tells geoPoint what to put on the x-axis, what to put on the y-axis. So you can try, for example, switching these two and seeing what happens. You'll just get a plot with them on the other way around. There are these 5 points out here that I've colored in red that, maybe this one too, but at least these ones, they kind of stand out from the rest. So what are they? What if we want to kind of try to explain something about why those cars don't follow a trend? So we can replot data, this time color-coding each dot by the class of the car. And class is one of the variables in our data frame. Is it a two-seater? Is it a compact, mid-size, minivan, pickup, subcompact, or SUV? And so the different classes are now color-coded. And the way we did that is we just simply added this command, color equals class, to this aesthetic command. Plot displacement on the x-axis, highway on the y-axis, and then make the color of each dot equal the class of the car. And now we can see those 5 data points correspond to a two-seater sports car. So they stand out. They have a big displacement, they have a big engine, but they're not as bad in terms of fuel efficiency as the other cars with a big engine. They have a bit better fuel efficiency, even though they have a big engine. Why do you think that is? Why would a sports car have better fuel efficiency than other cars, even though it has a big engine? They're lighter, exactly. Yeah, so the power to weight ratio is better. That. These are probably all massive, massive SUVs that are heavy. So we can color code by another variable really easily by just asking it to color code by, whatever variable in the data frame you want. We can change the size of the dots by adding another command, size equals 3. This is all within the geoPoint command. I don't know what the default is, maybe 1. But if you change it to 3, they get bigger. Now, just notice something, that for the color command, we added it within this AES bracket. Displacement on the x-axis, highway on the y, and color equals class, that's all within those brackets. If we were to put color equals class outside of those brackets, we would get this. No, sorry, I got it the wrong way around. If we were to put size, which is outside the bracket, inside the bracket, we would get that. Now we would get the size of each point depends on the class of the car. So these ones are small, those ones are big. If we put it outside of that bracket, then they're all the same size. So within this bracket, we're basically asking for features of the plot that we want to change depending on the value of one of the variables. If we put it outside the bracket, we're basically saying, I want it to be this color or this size, no matter what, for everything. So if you want things to depend on a variable, they have to go within that bracket. If you want it to be a constant value across the whole data set, it goes outside the bracket. You can play with that afterwards to see how it works. I just wanted to point it out. You can also do things like add transparency by changing the alpha value. And I'm just showing you a couple of the features. There's a whole giant laundry list of possible changes you can make. Here's another, well, any questions first before I go on? Yeah.
So you said if you go outside of the brackets, you can define specifically, like say for example, what's the color you want for
Yeah.
a variable. So then can you do it where some of them are randomly colorized, but then like one of them is like a specific color?
Oh, I see. That's a weird question. So, could you make sure that one class of cards is a particular color, and the other ones are randomly colored? Mostly when there are questions like that, the answer is yes, you can. The follow-up question, how do you do it? If you gave me half an hour, I could probably figure it out. But yes, you could do that. I think the short answer is you can do anything in ggplot. The more conventional things you can do easily and quickly, and then the more customized it gets, the more customized your code might have to get. But yeah, you could probably do that. Well, like for example, here I plotted the two-seaters in red and everything else in black. And I don't remember what the code for that is somewhere. I should show it here. But yeah, so it's possible. Other questions? Yes.
So when it was outside of the brackets, you defined size with 3, but when it was inside, you put size equals class.
Right.
So, like...
Yeah, so when it's outside the bracket, what I'm saying is I want all of the points to be size 3. Right? When it's inside the brackets, the fact that it's inside the brackets means that I want the size to be determined by the value of some other variable in the data frame.
So
in the table.
if you put size equals 3 inside the brackets, it wouldn't work?
Do you have it out there?
No, I haven't downloaded it yet, so I'm just curious.
I think, what would it do? Does anyone have it up? Can they try it? Put size, do this, but put size equals 3. I think it might complain, because I think it might be expecting a variable name, not a constant value, but I'm not sure.
Gives you an error.
It gives you an error. What does it say?
Unexpected.
Unexpected something.
Yeah. Greater than in. Like greater than something.
Yeah, the error messages are not always very informative, but I think that's what it's trying to say, is that it's expecting a variable name, but you're doing a constant. Other question back there? Yeah.
I tried it and I didn't get an error. I just got an extra legend on the side that says size.
Oh, interesting. So you didn't get an error, but it didn't do exactly.
It doesn't change the.
Doesn't change it. Okay. Okay. Maybe it's a different version of R. I'm not sure. Yeah. But you understand the main concept. Okay, good. Other questions? Okay, you know what? It's been an hour. In the class, we have 2 hours if we wanted. Why don't we take a 5-minute break? And then we'll do a little bit more graphics, and then we'll look at the homework. Okay, so let's take a